Module 7 Ethernet switching. Ethernet operates in the data link layer and the physical layer. It is a family of networking technologies defined in the 802.2 and the 802.3 standards. It supports data bandwidths of the following, anything from 10 megs to 100 gigabits and beyond. It is divided into two sublayers. The data link layer has two sublayers, the 802.2, which is the logical link, and the MAC, media access control layer. So Ethernet itself is a standard that defines LAN technologies. Here you see that 802.3 is the all-encompassing standard for Ethernet, and then 802.2 is actually the standard that defines the logical link layer of the data link layer. The 802 LAN/MAN standard, so LAN meaning local area network, MAN meaning metropolitan area network. So think of something like a Citizens Bank that has numerous locations in one city or town. So those standards, including Ethernet, use two separate sublayers of the data link layer to operate. So your logical link sublayer, 802.2, places information in the frame to identify which network layer protocol is used for the frame. Your MAC sublayer, defined as 802.3, 802.11, or 802.15, is responsible for data encapsulation and media access control and provides your data link layer addressing. So in the graphic that you see here, you see them kind of split out into different functionalities. So data link layer in totality has those two separate sublayers. Logical link is defined in the standard of 802.2. Your MAC sublayer has all of those different standards that are Ethernet. So the all-encompassing is 802.3 for Ethernet. Okay, and then you see them broken out. So 802.2 is your logical link layer. WAN is 802.11, your wireless. YPN is 802.15, your Bluetooth. Your various Ethernet standards for fast Ethernet, gigabit, etc. And then under your WLAN, you have various WLAN standards for different types of wireless communications. So don't forget the others that we learned about. We learned about Zigbee and we learned about WiMAX. And then various YPN standards for Bluetooth, RFID, etc. So if you've forgotten some of those, go back and revisit those slides in the previous chapter. Now the MAC sublayer is responsible for data encapsulation and accessing the media. Data encapsulation, defined under 802.3, includes the following: your Ethernet frame. So this is the internal structure of the Ethernet frame after it is passed down from the network layer as a packet of information. So at the data link layer, it is going to get Ethernet addressing. So the Ethernet frame includes both a source and destination MAC address to deliver the Ethernet frame from the Ethernet NIC to the Ethernet NIC on the same local area network. So whenever you're thinking about local area network communication and frame delivery, you want to be talking about your switch. It also includes that Ethernet error detection. So remembering that the Ethernet frame includes a frame check sequence trailer. Within that trailer is a CRC value, cyclic redundancy check. So as a source is generating information, it is doing a mathematical algorithm that is generating this value. Now you don't need to know how that algorithm works. Just know that it creates this value known as a CRC. It places that value into this trailer, and at the destination, as it is being unwrapped, it is also doing its own calculation and comes up with a value. If those two values match, it is then passed up the stack for processing. If they do not match, then that frame is dropped. And that is your error detection component. Media access. IEEE 802.3 is your MAC sublayer. MAC sublayer of the data link layer includes the specifications for different Ethernet communication standards over various types of media, including copper and fiber. So when you talk about legacy networking, you're talking about using a bus topology. So within your bus topology, it is a shared medium, meaning every single device is contending for that connection to, excuse me, to the Ethernet. It is shared half duplex. So Ethernet over half duplex medium uses a contention-based access method, defined as carrier sense multiple access collision detection. So when two frames collide on the medium, a collision will happen. A collision will be noticed by everybody else on that medium. So think back to how we defined our ones and zeros. So if we say a 1 in the copper world would be 5 volts, then a collision in that environment could be something, could simply be something just above 5 volts. So anything above 5 volts, all your end devices are going to go, whoa, hey, a collision happened. So what they do is they do this back off algorithm. So they will back off for a certain amount of time, and they will let things get settled. So they'll back off. The amount of time that they back off is inherent to whatever operating system is on the device itself. But they will be different intervals for each end device, because clearly if they all restarted at the same time, a collision then again could happen. Now the two frames that collide still continue to their destination, but at their destination, what's not going to match? That CRC value. Because also at the destination, your end device does that mathematical algorithm. It creates that CRC value. It checks it against the one that is in the FCS trailer field. If they match, it is processed. If they don't match, it is dropped. So if two frames collide, would you assume that their information would be different? Of course it would. So those values are not going to match. They will be considered corrupt, and they will be dropped. Your Ethernet LANs of today use switches that operate in full duplex. Full duplex communications with Ethernet switches do not require access control through CS&ACD. So think back when you made your cables. When you made your crossover cables, you had two sets of wires that crossed over. You had 1 and 3 and 2 and 6. So if I am transmitting on one wire and receiving on the other, then a collision will not happen. Now in this graphic on your right, just pay attention to the different breakouts of your Ethernet standard. So again, the standard in totality is 802.3. Okay. Then your logical link sublayer in the data link layer is Ethernet 802.2. And then your cabling. So as your cabling increases, there are sub-standards of Ethernet that are defined. So fast Ethernet 802.3U, gigabit Ethernet over fiber 802.3Z, gigabit Ethernet over copper, again 802.3AB, 10 gigabit Ethernet over fiber 802.3AE. And that will continue up to your, higher gigabits, terabytes. All of those will be defined in subdivisions of the Ethernet standard. Now, within your frame fields, there are parameters that you need to be familiar with. So you need to get a good understanding of these terminologies on this slide itself. The minimum Ethernet frame size is 64 bytes. So that means if a frame is at least 64 bytes large, it is considered valid. So it would be processed. The maximum is 1518 bytes. Your preamble field is not included. So your preamble field is your synchronization. So that is the start of your frame. So as you see down here, SFD is start frame delimiter. So this is the start of your frame. So that is your preamble. That is not included when describing the size of the frame. So any frame that is less than 64 bytes in length is considered what we call a collision fragment or a runt. They are automatically discarded. Frames with more than 1,500 bytes of data are considered jumbo or baby giants. They are also discarded. If the size of a transmitted frame is less than the minimum or greater than the maximum, your receiving device will simply drop the frame and not even bother to try and process it. Dropped frames are likely due to the result of collisions and other unwanted signals. They are considered invalid. Jumbo frames, however, are usually supported by most fast Ethernet and gigabit switches and their NICs. So down here again, you see you have your destination MAC address, you have your source MAC address, you have your type and length, you have your data, which is what is you're doing. Your type and length would be what is the networking packet coming down from the network layer. Your data is, again, what is it you're doing, and then your FCS is your error detection field. So this slide here is basically just describing those different fields. So again, your preamble and starter frame delimiter fields. It is 7 bytes of information. It is also called the starter frame, which is 1 byte, used for synchronization between the sending and the receiving devices. So the first 8 bytes of the frame are used to get the attention of the receiving node. The first few bytes tell the receivers to get ready to receive that frame. Your destination MAC address, pretty self-explanatory. It is a 6-byte field, and it is the identifier for the intended recipient. Your source MAC address, again, 6-byte field, identifying the original NIC or interface of the frame. Your type or length is a 2-byte field. This identifies your upper layer protocol that is encapsulated into that frame. So in hexadecimal values, 0x800 identifies an IP4 packet. 0x86DD identifies an IP6 packet. 0x806 will identify an ARP packet. You may also see this field referred to as ether type, or length, all interchangeable. Your data field is a field from 46 to 1500 bytes. This is going to contain the encapsulated data from a higher layer, which is a generic layer 3 PDU, or for our references, your IP4 packet or IP6. All frames must be, again, at least 64 bytes long. If a small packet is encapsulated, additional bits need to be added. That's called padding. So you would pad up to the size of 64 so that it is considered valid. So the only really way to describe that process is anybody who's ever done web design, when you have, let's say, an image and you need it to fit a certain size on your web page, if that image isn't large enough, you have to put kind of padding fields in order to make it the correct size. Think of putting something into a shipping box, and so you don't want it to rattle around, you put in all that bubble wrap. So you pad it up enough so that it fills that space so that it is considered good. Same type of thing here in the data world. Now your frame check sequence field. This is 4 bytes of information and is used to detect errors in a frame. It uses, again, that cyclic redundancy check. So the sending device includes the result of the CRC in the FCS field of the frame. The receiving device receives that frame, generates a CRC to look for errors. If the calculations match, it is considered error-free. If the calculations do not match, there is an indication that that data has changed, therefore the frame is dropped. And again, a change in data could be anything from a disruption of service, electrical signals, those two different interferences, RFI and EMI that we talked about previously. Now, an Ethernet MAC address consists of 48 binary bits, expressed as 12 hexadecimal values. Given that 8 bits, which is referred to as 1 byte, is a common binary grouping, so binary all zeros to binary all 11s can be represented in hexadecimal as the range of 00 to FF. So think back to your conversions that we just went over. When using hexadecimal, your leading zeros are always displayed to complete the 8-bit representation. For example, the binary value 00001010 could be represented as 0A. And again, do the conversions in order to see how you get there. Hexadecimal numbers are often represented by the value preceded by 0x. So as an example, if you see 0x73, you know it's a hexadecimal digit. If you see simply 73, you know that it is a decimal digit. So this is how you distinguish between decimal and hexadecimal values in documentation. Excuse me. Hexadecimal may also be represented by a script 16 or the hex number followed by a capital H. So in an Ethernet LAN, every network device is connected to the same shared media. Your MAC addressing provides a method for device identification at the data link layer of the OSI model. An Ethernet MAC address, excuse me, is a 48-bit address which is expressed using 12 hexadecimal digits, as you see here. Because a byte equals 8 bits, we can also say that a MAC address is 6 bytes in length. All MAC addresses must be unique to the Ethernet device or the Ethernet interface. To ensure this, all vendors that sell Ethernet devices must register with the IEEE to obtain a unique 6 hexadecimal number, which can be referred to as either a 24-bit or 3-byte code, which is referred to as the organizationally unique identifier, or the OUI. An Ethernet MAC address consists of 6 hexadecimal vendor OUI codes, followed by 6 hexadecimal vendor assigned values. So think of your OUI as something like whether Realtek developed the NIC card, or Cisco developed the NIC card, or Intel, whoever is the manufacturer of the card is the vendor assigned. The organizationally unique identifier is the one that is assigned by IANA. So, IEEE. So IEEE would assign this part here which identifies the organization. This part here is the organization. Assigned. So as an example, if Intel, and this is just an example, it's not verbatim, if Intel was assigned every single NIC card that Intel created would have that. Your uniqueness, okay, that they talk about here, your unique identifier would be, now Intel has that, but the last 6 bytes, okay, are assigned, excuse me, last 3 bytes are assigned by Intel themselves. So PC1 would have this and a unique identifier. PC2 would also have this and its own unique ID. So that is the uniqueness. So first portion assigned by EEE to a particular vendor. Second portion, organizational assigned, where the first 6 will be the same for everything made by that organization. And the last is the unique identifier. So how are frames processed? When a device is forwarding a message to an Ethernet network, the Ethernet header includes a source MAC address and a destination MAC address. When a NIC receives an Ethernet frame, it examines the destination MAC address to see if it matches the physical MAC address that is stored in RAM. If there is no match, the device will discard the frame. If there is a match, it passes the frame up the OSI layers where the de-encapsulation process will take place. Note, your Ethernet NICs will also accept frames if the destination MAC address is a broadcast or a multicast, of which the host is a member. Any device that is the source or destination of an Ethernet frame will have an Ethernet NIC and therefore a MAC address. This is going to include your workstations, your servers, your printers, mobile devices, and let's not forget our routers, because they are our default gateway. Now, what I want to point out to you on this slide is, when you're talking about an Ethernet frame, so in a frame, I want you to keep this in the back of your head until we talk about the networking layer. In a frame of information, your destination address comes first. Okay? I'm going to talk about why that is. Again, your encapsulated data is coming down from the network layer. And then this information is placed on the front, and then that frame check sequence, your trailer, would be placed here. Okay? But try to remember, in a frame, destination address comes first before the source. Now, in Ethernet, different MAC addresses are used for layer 2 unicast, broadcast, and multicast. You need to be familiar with these. A unicast MAC address is the unique address that is used when a frame is sent from a single transmitting device to a single destination device. The process that a source host uses to determine the destination MAC address associated with an IP address is known as address resolution protocol. And we will talk about that in Module 13. The process that a source host uses to determine the destination MAC address associated with an IP6 is known as neighborhood discovery. The source MAC address must always be a unicast. So now I want you to stop paying attention to these graphics going forward in understanding the information that is in them. Okay, so now I was said to wait until the networking module, but we can see it right here on this slide. So this is encapsulation. This is this thing I draw on the board for you every single week, right? Mostly. So you have, again, your data. Which is, what are we doing? That comes down from application, presentation, and session. Then you get to your network layer. Your network layer puts in a source IP and a destination IP in its header. Then it comes down to the data link layer. Your data link layer puts in a destination MAC address and a source MAC address in its header. And in the trailer, in the frame check sequence field, it puts that CRC value for error detection. So what you notice in this, or what I hope you notice in this graphic, is that for your routers, the source IP is first. For your switches, the destination MAC is first. And we'll talk about why that is as we go forward. Now, an Ethernet broadcast frame is received and processed by every device on the Ethernet LAN. So the features of an Ethernet broadcast are as follows. It has a destination MAC address of FFFFFFFFFF in hexadecimal, 48 ones in binary. It is flooded out all Ethernet ports except the incoming ports. Okay? Except the incoming port. It will never, which is referred to as an egress. Ingress. Okay? It will never send it back out the port that it was received from. It is not forwarded by a router. Very important. Routers do not pass broadcasts. They contain broadcasts. Okay? If the encapsulated data is an IP4 broadcast packet, this means the packet contains a destination IP4 address of all ones. Now think back to your binary. If I convert all ones from decimal to all ones in hexadecimal, we should all agree that it is definitely going to be Fs, right? Because I'm using all 4 bits. 8 plus 4 plus 2 plus 1 is 15. 15 in hexadecimal is an F. This numbering in the address means that all hosts on that local network, or what is referred to as a broadcast domain, will receive and process the packet. In Ethernet multicast frame, is received and processed by a group of devices that belong to the same multicast group. So thinking back, when you're doing multicasting, you create the group, and then you assign end devices to that group. There is a destination MAC address of 01005E when the encapsulated data is an IP4 multicast packet. So you need to know that. And a destination MAC address of 3333 when the encapsulated data is an IPv6. So again, in this picture here, I am sending an IP4 packet. Okay? Because I am seeing 01005E 0000C8. Now, understand, this is a multicast. And go back to your, I know we kind of touched base a little bit on IP addressing and those classes of addresses, but hopefully some of you remember that the multicast group started with 224, which would we all assume does start with 224. So this is also a multicast. Okay, so you have to be able to equate these things when you're looking at these slides. And again, understand 0000C8, for those of you who might pick it up quickly, is simply the conversion of 0.0.200. Okay, if you can't see it, do the conversion. Okay, it is just simply that. You have to understand that when you're looking at these depictions, it's important information that you want to be able to pick up on. Okay, don't just idly go by and say, "Ooh, pretty picture." Understand what the picture is telling you. So up here, like in the last one, I didn't point this out, but here it is a multicast, right? So in this depiction up here, you have a single source that is sending it out to only a few in that host group. The other two are not included in that host group, so they do not receive the multicast message. Now, there are other reserved multicast destination MAC addresses for when the encapsulated data is not IP, such as Spanning Tree Protocol, STP. You're going to learn about STP in the next course, but just at this juncture, understand that there are other reserved multicast destination MAC addresses. For you, for now, you want to know the two that are depicted on this slide for IP4 and IP6. So it has flooded out all Ethernet switch ports again, except the incoming port. Unless the switch is configured for multicast snooping, which is again something we'll talk about way later. It is not forwarded by a router. Routers do not pass broadcasts unless the router is configured to route multicast packets. Again, future networking. Because multicast addresses represent a group of addresses, sometimes called a host group, they can only be used as the destination of a packet. So whether you are a unicast, multicast, or broadcast, you are just one generating source. You will always be a unicast at the source. Now, as an example, you're going to find that these messages will interplay with each other, meaning I have a device that came in. You walked on CCRI campus with your laptop. Your laptop, when you turn it on and try to search the internet, immediately is screaming out for IP configuration parameters. Well, chances are CCRI has more than one DHCP server, Dynamic Host Control Protocol, which is responsible for assigning IP configurations. So your message may go out as a broadcast saying, hey, what server can give me the information that I need? When a server responds to that message, however, it comes back as a unicast because it is only going to the generating source. So you will see them interact with each other in different ways. As with the unicast and broadcast addresses, the multicast IP address requires a corresponding multicast MAC address, as you see in this graphic. A layer 2 Ethernet switch uses layer 2 MAC addresses to make forwarding decisions. It is completely unaware of the data or the protocol being carried in the data portion of the frame, such as whether it's an IP4 packet, whether it's an ARP message, or whether it's an IPv6, does not care. The switch makes its forwarding decision based solely on the layer 2 MAC address. An Ethernet switch examines its MAC table to make a forwarding decision for each frame, unlike legacy Ethernet hubs that will repeat bits out all ports except the incoming port. So your switches are making decisions. Your hubs in older technology did not make decisions. They just flooded whatever it received out every single port that has something attached to it, except the incoming ports. So when a switch is initially turned on, the MAC address table is empty. Your MAC address table is also sometimes referred to as a content addressable memory table or a CAM table. So here you say, I do have 4 devices that are attached to my switch ports. However, my MAC address table is empty because it is not populated yet with information. So how do switches learn and forward? Your switches examine source MAC addresses only to create this table. Okay, every frame that it enters a switch is checked for new information to learn. It does this by examining the source MAC address of the frame and the port number where the frame entered the switch. Excuse me. If the source address does not exist, it is added to the table along with the incoming port number. This is the only parameter your switches use to build those tables. If the source MAC address does exist, the switch updates the refresh timer for that entry. By default, most Ethernet switches will keep an entry in their table for 5 minutes. And again, this is dependent on the iOS that the switch is running. Note, if the source MAC address does exist in the table, but on a different port, which could happen, I remove one device from a port, I plug it into another one, whether purposefully or in error, your switch treats this as a new entry. So the entry is replaced using the same MAC address, but with the more current port number. Now, finding the destination MAC address, this is referred to as forwarding a frame of information in a switch. If the destination MAC address is a unicast, the switch will look for a match between the destination MAC address of the frame and an entry in its MAC table. If the destination address is in the table, it will simply forward the frame out that specified port. If the destination MAC address is not in the table, the switch will forward the frame out all ports except the incoming port. This is known or called an unknown unicast. Now, if the destination MAC address is a broadcast or a multicast, the frame is also flooded out all of the ports except the incoming ports. And again, when we say all of the ports, we mean all of the ports that something is attached to. So in this example, if I am looking at this example, if PC1 that you see here in the MAC address table, it's listed, is sending information to PC4, excuse me, it simply goes from 1 to 1. So first scenario, PC1 talking to PC4. Looks like this. This is the source. So it goes up, switch does its thing, it says, oh, I have an entry for 4. Send it over and out 4 to the destination. I just realized that orange arrow was there, so I might be doing a different example than what they're showing you here. However, if PC1 is going to talk to, let's say, or PCA, I said 1 and 4. Let me change that so you're not confused. So, in the second scenario, PCA is still my source. And now I'm going to try to talk to PCC. So again, my source is here. I get up to the switch. The switch says, oh, I don't have that in my table. So it floods it out. Now for this example, it's going to flood it out ports 2, 3, and 4, but not port 1, because port 1 is where it was generated from. So it sends it out to these 3 ports. Now, only the PC that has that destination, or has that not Ethernet, I apologize, that MAC address will respond back to the message. So what do you think happens here? Go back. We said that the only way a switch generates a table entry is from a source machine. Would you not agree that when PCC answers that request, it is now the source machine? So, PCC answers the request because that is its destination MAC address, or its MAC address. The switch gets that. So now PCC is the source answering the request. Your switch gets that, and your switch says, oh, hey, I learned new information. I know now that port 3 has a MAC address of OOOB. Now the encapsulation can be completed, and PCA can now forward the information to PCC. So this is how your switches build their tables and make their decisions. So in going through it, as a switch receives frames from different devices, it is able to populate its MAC address table by examining the source MAC address of every frame. This, again, is the only parameter used by that switch. When the MAC address table of the switch contains the destination MAC address, it is able to filter the frame and forward it out a single port. So in my previous example, if PCA is sending information to PCD, it simply goes from port 1 and out, received in port 1, ingress, and received out port 4, egress, directly to PCD. So a unicast one-to-one communication. Switches use one of the following forwarding methods for switching data between network ports. First one you're going to learn about is store and forward switching. This frame forwarding method receives the entire frame and actually computes that CRC value. If the CRC is valid, the switch will look up the destination address, which determines the outgoing interface. Then the frame is forwarded out of the correct port. So when you're looking at those tables in the previous two slides, you have the attached device, and then you have the ports associated with each device. In your cut-through switching, this frame forwarding method forwards the frame before it is entirely received. At a minimum, the destination address of the frame must be read before the frame can be forwarded. So think back a couple of slides when I said, gee, why do you think the destination address comes first for a switch? This is why. Because in cut-through, as soon as the switch knows the destination address of the frame, it will start to forward that frame. A big disadvantage of storing forward switching is that it determines if a frame has errors before propagating the frame. So that is a huge advantage. So if I do that error check before I push my frame out, I know the frame is good. With cut-through switching, you could have some errors because there is no checking. So when an error is detected in a frame, the switch will discard that frame. Discarding frames with errors reduces the amount of bandwidth consumed by corrupt data. So store and forward switching is required for things like quality of service analysis on converged networks, where frame classification for traffic prioritization is necessary. You will learn about classification and prioritization in Cisco 3. For now, just understand that store and forward is required if you implement quality of service in your network. As an example, voice over IP data streams need to have priority over something like web browsing. Now, in cut-through switching, the switch acts upon the data as soon as it is received. So even if the transmission is not complete, your switch will buffer just enough of a frame to read that destination MAC address so that it can determine to which port it should forward out the frame. Again, cut-through does not perform any error checking on the frame, so you could pass corrupt frames. There are two different variants of cut-through switching. First one is fast-forward switching. This offers the lowest amount of latency because it immediately forwards a packet after reading the destination address. However, what do we know? It could pass corrupt frames. So what you're giving up for passing these corrupted frames? Speed. Cut-through switching is going to be a lot quicker. Think back to store and forward. Store and forward had to receive the entire frame, do that CRC, and then push it toward the destination. Here, the only thing that fast-forward switching needs is the destination address. So it is the lowest level of latency. So again, because fast-forward switching starts forwarding before the entire packet has been received, there may be times when packets are relayed with errors. The destination NIC, again, would do what? It would do that CRC value check. So they're still going to be dropped at the destination. because of that FCS field with the CRC value in it. Fast forward switching is the typical cut-through method of switching. Now, the middle line between store and forward and fast forwarding is fragment free. So a compromise between the high latency and the high integrity of store and forward and the low latency and reduced integrity of fast forward, the switch stores and performs an error check on the first 64 bytes. And why 64 bytes? It is the minimum size of a valid frame. Okay, so fragment free says, I'm going to check at least the 64 bytes, which I know is the minimum size for a valid frame. If that's good, I'm just going to push it forward. Because most network errors and collisions also occur during the first 64 bytes, this ensures that a collision has not occurred before forwarding this frame. So you have store and forward, most reliable, but creates the most latency because it does an error check on the entire frame before forwarding it out. You have cut through that just says, tell me where I'm going, and I'm going to stop forwarding. So lowest latency, but unreliable frames can be passed. And then you have fragment free, which is your middle ground that says, I'm not going to check the whole thing, but I'm going to check the first 64 bytes because I know that that is the minimum size for a valid frame. So an Ethernet switch may use a buffering technique to store frames before forwarding them or when the destination port is busy because of congestion. So there are two different methods that can be chosen. There is port-based memory, and then there is shared memory. So within port-based memory, frames are stored in queues that are linked to specific incoming and outgoing ports. A frame is transmitted to the outgoing port only when all the frames ahead in the queue have been successfully transmitted. And we refer to that as FIFO. First in, first out. Now, it is possible for a single frame to delay the transmission of all frames in memory because of a busy destination port. This delay occurs even if the other frames could be transmitted to open destination ports. So port-based kind of looks like this. You have a switch. With some ports. Well, first conversation, port 1 wants to talk to port 4. So what they do is they create what is referred to as a virtual circuit, a connection in software, where port 1 lines up right at port 4. Now, coincidentally, 3 also wants to speak to 4. So 3 creates a virtual circuit. And it lines up right behind port 1. So 3 has to wait for 1 to go FIFO before it can be next in line. So that is a port-based example. Now, our other example says shared memory. Within shared memory, it deposits all the frame into a common memory buffer shared by all switch ports. And the amount of buffer memory required by a port is dynamically allocated. The frames in the buffer are dynamically linked to the destination port, enabling a packet to be received on one port and then transmitted on another port without moving it to a different queue. So shared memory within your switch, I still have my 4 ports, but now I have this shared buffer here. And one still wants to talk to 4. So 1 to 4 goes in that shared buffer. 3 still wants to talk to 4. So 3, 4 also goes in that shared buffer. And when that port is free, then they will get pushed out. So shared memory buffering also results in larger frames that can be transmitted with fewer dropped frames. This is important with asymmetric switching, which allows for different data rates on different ports. So the more you learn about your switches, you'll see that a particular port can run at 10, 100, or 1,000. It all depends on the parameters of the switch. So, and that's called port density. So when we get a little bit further into this and we start talking and looking at switches and routers, those are things you need to pay attention to. What type of speeds do I need available on my switch ports in my local area network? More bandwidth can be dedicated to certain ports, something like a server port, where you would have multiple other devices trying to speak to that one port. Now, two of the most basic settings on a switch are the bandwidth, referred to as speed, and duplex settings for each individual switch port. It is critical that the duplex and bandwidth settings match between the switch ports and the connected devices. Again, looking back, there are 2 different types of duplex. There is full duplex, where both ends of the connection can send and receive simultaneously. And then there's half duplex. Only one end of the connection can send at a time. So looking back at your symbols, okay, your full duplex looks like this, and your half duplex will look like this. Now, order negotiation is an optional function found on most Ethernet switches in NICs today. It enables 2 devices to automatically negotiate the best speed and duplex capabilities. So, what happens here, if you set them both to auto-negotiate, they will auto-negotiate the connection themselves. But if something were to happen and some parameter changed, it could be that the one connection that used to be a full duplex connection at the destination is now only a half duplex connection. This is referred to as a duplex mix match. Giganet ether ports only operate in full duplex, so you don't see the scenario. But in older technologies, you can see this happen. So a duplex mismatch is one of the most common causes of performance issues on a 10-100 megabit Ethernet link. It occurs when one port on the link operates at half duplex, while the other port operates at full duplex. This can occur when one or both ports on a link are reset, and the auto negotiation process does not result in both link partners having the same configuration. It can also occur when users reconfigure one side of the link and forget to reconfigure the other. So we can actually go into our switch ports and tell our switch ports what speed to work at and what duplex to work at. Excuse me. So take a scenario where you had an older situation. So you had a switch port that was connected to a hub because that's what you had available in your network. So you would actually have to go in and tell the switch port that was capable of full duplex that, hey, I know you're capable of this, but I need you to run it this, because you have to talk to this piece of equipment that is plugged into you that can only run at 10 megabytes. Okay, so you would have to go in there and create that yourself, or you would end up with a duplex mismatch and nothing would happen between those two ports. So best practice is to configure both Ethernet switch ports as full duplex where applicable or appropriate. So connections between devices once required the use of either a crossover or straight through cable. And I've talked to you about this before, this auto MDIX feature. Okay? And I've also told you in my classroom, you need to know which type of cable to use for which scenario. So the type of cable required depended on the type of interconnecting devices. A direct connection between a router and a host requires a crossover cable because it is a NIC-to-NIC communication. Most switch devices today will support the automatic medium-dependent interface crossover feature, auto MDIX. When this is enabled, your switch will automatically detect the type of cable attached to the ports and configure the interfaces accordingly. The auto MDIX feature is enabled by default on switches running iOS 12.2 and above. However, understand that this feature could be disabled. So if a technician goes in there and disables this feature and you use a straight through cable in a connection that should be a crossover cable, you will not have communication, which is why I say you should always use the correct cable type and not rely on the auto MDIX feature. Now, I'm sure out in the production industry, this is different. They don't adhere to these rules like in my classroom. But I'm telling you, in my classroom, I want you to know the difference between your cables, okay? Auto MDIX can be re-enabled using the MDIX auto interface configuration command. However, it can also be disabled. So if it is disabled and you don't know what type of cable to use, you're not going to look that smart. And again, as I always point out, mom and pop scenarios may not have the ability to purchase the latest and greatest of equipment that have these new iOS implementations. Okay, so again, know your cables and what they do. Crossover, we should know by now. Okay, like devices. Switch to switch. Router to router. And router to PC because it is NIC to NIC. Straight through cable. Unlike devices. So switch to router. Also switch to PC as you see down here. And again, crossover cable, NIC to NIC. So your like devices. And that will do it. I will see you in class when I see you.